A massive star spends its life in a delicate balancing act, generating outward pressure through nuclear fusion to fight off the crushing inward pull of its own gravity. When that nuclear fuel finally runs out, gravity immediately takes over, and the core of the star collapses. The gravitational pressure becomes so intense that it overcomes the electrostatic forces that normally keep atoms apart. Negatively charged electrons and positively charged protons are violently crushed together, forming a dense sea of neutral particles. The result is a core containing twice the mass of our Sun, compressed into a sphere no wider than Manhattan. This collapse only stops when the newly formed neutrons pack so tightly together that quantum physics strictly forbids them from getting any closer, a phenomenon known as neutron degeneracy pressure. What remains is the densest solid matter in the known universe. It creates a gravity well so deep that ordinary physics distorts. Dropping an object from just a few feet above the surface means it would hit the ground traveling millions of miles per hour. As the original star collapses, its magnetic field is also compressed and amplified. In a rare variation of a neutron star known as a magnetar, this process generates a magnetic field a quadrillion times stronger than Earth's. The rigid outer crust of the neutron star, made of densely packed iron nuclei, is physically locked together with these intense magnetic field lines. When the magnetic field shifts, the crust goes with it. The resulting rupture is called a starquake. A single fracture can release more energy in 1/10 of a second than our Sun has emitted over the last 100,000 years. If two of these extreme stellar remnants orbit each other in a binary system, their gravity distorts the fabric of spacetime. They radiate energy outward as gravitational waves, which forces the stars to spiral closer and closer together. In their final orbits, whipping around each other at a significant fraction of the speed of light, their magnetospheres physically interact. The magnetic field lines connect, break, and snap back, accelerating surrounding plasma to relativistic speeds. This high-speed orbital dance is a countdown. The two stars are hurtling toward a violent collision that will forge entirely new matter and scatter it across the galaxy. Traveling at roughly 30% the speed of light, the two neutron stars collide. The resulting explosion is called a kilonova. It shines 1,000 times brighter than a standard nova, powered entirely by the radioactive decay of new atomic nuclei created in the blast. The sheer impact of the collision shatters the neutron stars, ejecting large quantities of neutron-rich matter outward into the surrounding vacuum. In the days following the blast, the expanding debris cloud cools. As it expands, the light radiating from the explosion noticeably shifts from bright blue and violet into deep red and infrared wavelengths. By analyzing the specific colors absorbed by that cooling debris, astrophysicists can identify exactly which elements are present. This color shift provides the physical proof that heavy metals are being actively forged in the wreckage. Normal stars act as stellar furnaces, fusing light elements together, but they stop at iron. Trying to fuse elements heavier than iron consumes more energy than it produces, which inevitably kills the star. To forge the heaviest elements in the universe, you need a process that bypasses normal stellar fusion. This is known as the rapid neutron capture process, or R process. In the R process, an atomic nucleus is bombarded by free neutrons, capturing them so rapidly that it physically bulks up. Being highly unstable, it undergoes beta decay, transforming a neutron into a proton, instantly creating a brand new, heavier element. The yield from these collisions is staggering. Observations of the 2017 kilonova confirmed that a single merger produced enough solid gold to equal 10 to 20 times the mass of the Earth. A neutron-star collision provides both the extreme energy and the dense cloud of loose neutrons required to execute the R process and finish building the periodic table. Once forged, these newly minted elements are blasted outward at millions of miles per hour, riding the shock wave of the kilonova into the surrounding interstellar medium. Over millions of years, these elements drift through space until they eventually slow down and settle into massive, cold clouds of cosmic gas and dust. As gravity eventually causes these enriched clouds to collapse and form new solar systems, the heavy metals are swept up and incorporated into the crusts of newly forming planets. This means the materials we rely on today have a violent cosmic lineage. The gold in this jewelry, the platinum in industrial catalysts, and the iodine circulating in our blood were all forged in the collision of dead stars. Every gram of these heavy metals found on Earth is physical evidence of a stellar crash that happened billions of years before our solar system even existed. Beyond seeding planets with heavy metals, kilonovae possess a unique physical trait. Their explosions expand outward in an almost perfectly spherical shape, unlike the asymmetrical, messy debris left behind by standard supernovae. We can see how this helps astronomers in this diagram. Because the expanding fireball is highly symmetrical, scientists can use it as a standard candle. They can compare the apparent visual size of the sphere as seen from Earth to the actual physical velocity of the expanding gas. By calculating the difference between how large the explosion appears and how fast it is actually growing, astrophysicists can determine exact distances in space, allowing them to measure the Hubble constant, the rate at which the universe is expanding. In the 2030s, next-generation gravitational wave observatories like LISA will listen for the low-frequency signals of binary neutron stars, tracking them millions of years before they collide. Neutron star mergers provided the raw materials necessary for planetary geology and human biology. Now, by tracking their explosions, they offer us a precise tool to measure the scale, age, and ultimate geometry of the cosmos itself.